the transformer. To motivate the transformer, I want to remind you that we had, with recurrent neural network models, we had a fixed dimension, finite parameter model that could propagate information indefinitely into the future using this uniform representational space that was successively modified by incoming input. But it was hard to propagate information very far into the future from context for a number of reasons. One that you may remember is the problem of the vanishing gradient. So there are many different steps between a word that's far into the future or far into the past to get to a prediction far into the future. And every one of those has to pass through some nonlinear activation function. And if you're not careful, the gradient could be very small, and it would be very hard to propagate error signal from up here back many words distant in the context. If you're careful about the choice of the nonlinear activation function, then you can address that to some extent. But nevertheless, there's still a credit assignment problem, because if a word is very far back in the future, in the past, from a present word that is producing an error signal, then there are many words in between that word and the new word that appears that are competing for credit for, well, was I the word that was responsible for that new word coming up or not? And if a word is near in the context to the current word, then there's fewer words that it's competing with in some sense. And so even though clever choices of activation function helped with this problem, we still found that it was hard to propagate information very far into the future with the recurrent neural network model. Now, one thing that we didn't talk about very much, but is available with recurrent models, is stacking. So we can make recurrent models deep by stacking them. That means that we don't just use a single recurrent layer, but we add another recurrent layer, maybe arbitrarily many recurrent layers, as many as we want. And now the output prediction of what's the next word is coming from the end state of the final layer from the most recent word of the context. Abstractly, we can sort of think of each of these layers as doing some kind of transformation of the overall context. The transformation is still an RNN transformation. But it turns out that depth is actually often very useful for these deep learning models. In fact, in the case of computer vision, if you're familiar with this, depth was absolutely crucial to the success of current generation models. It turns out that depth buys you a lot in terms of successively transforming the input into greater levels of abstraction. Now, this depth is valuable in the RNN context. However, it doesn't solve the problem of input that's distant in the context from being far away. We still have the problem that a word that is not immediately before the next upcoming word still has to go through a lot of path steps in order to get connected with that word. And so there's a lot of steps back for back propagation and gradient information to flow. Conceptually, we'd like to do something that would maybe give words that are far in the distant in the context a bit more of a fair chance. And one way of visualizing what this would look like is we're going to move the next word prediction away from being so tightly associated with like the result of applying the last word, the most recent word in the context, and somehow make all context words equally distant from W sub I, from the next word. Conceptually, this might look something like this. So I've done two things. First of all, I've sort of made W sub I equally sort of far away or close to all of the context words at a conceptual level. And then the other thing you'll notice is that I eliminated the recurrent connections between words in each layer. And that's a really nice looking picture, but you can see that there's a potential risk, because now the words in the context are not connected to each other, and we run the risk of having some kind of bag of words-like behavior, where word order information doesn't matter. Words may not be able to interact in the appropriate way, in the way that language constrains us to do. And so now we have to ask, within each layer, how do words interact with each other in context? And you can see the transformer model as a way of answering this question for an architecture of the one that we have in front of us right now. To understand the transformer, I'm going to give you a bottom-up characterization of how it works. This bottom-up characterization is going to start from the words and show you what happens to the words successively. This is not the only way you can approach the transformer, but I think that for this expository purpose, it's maybe helpful. So let's imagine that we have the context like the dog ate the. And what you'll notice immediately is that we have two different instances of the same word. And conceptually, we need to distinguish those in some form so that the model doesn't treat them identically. In the transformer model, this is a very innovative and very different approach from what recurrent models had done, is that that's going to be accomplished by modulating the word embedding representation of each word in the input as a function of where it is in the context. So as before, we're going to have some kind of word embedding matrix. This is going to be learned. It has as many rows as there are vocabulary items, and it has some dimensionality. We'll call that D. And the first thing that we'll do is when a word is present in the context, we're going to look up its embedding representation. So if this is the row corresponding to the word the, then both instances of the word the will start off with that word embedding representation. But that's not what goes into the transformer model for modification. First, we get what is called a positional embedding representation. So in addition to this learned word embedding matrix, there is a fixed position embedding matrix, where now the rows are positions in the sentence indexed from 1 to arbitrarily high. So this is actually a matrix with infinitely many rows, but sentences are not arbitrarily long, and so the very, very high numbered rows get used rarely or never. You'll notice that each column here now looks periodic. It has periodic behavior. So the position embedding matrix columns, each of them is a periodic function. And so this means that the position embedding representation for each entry in the vector will look similar for different positions at particular offsets, but the offset will be different for each column. So just to give you a sense of how this works, so in this case, the first instance of the word the is in position 1, the second instance of the word the is in position 4. So for the first instance, we take the first row and we simply add it to the word embedding entry for the. And so when we sum these two things together, we get some other vector that you see on the left here above the vertical equal sign. For the second instance of the word the, this was the fourth word in the sentence. So we pull out the fourth row of this position embedding matrix and we add it to the word embedding for the, and we get out something now that's going to look somewhat similar to the embedding representation for the, but it's going to be a little different. So the similarity reflects the fact that they're both the word the difference reflects the fact that they're in different word positions. And so if the model, it turns out that the transformer model is able to leverage both of those things to great effect. The more general form of the position embedding function is that it's periodic of this form. The even number of columns are sine functions, the odd number of columns are cosine functions. The dimensionality that's actually used in the transformer model is 512, and you can see that it has periodic behavior, but it also distinguishes word positions out to an extraordinarily high degree, far longer than any sentence that you'll encounter in the real universe. So that's the input. That explains what comes into the model of this bottom layer. It's the sum of a word embedding representation with a positional embedding representation. So what happens at the layers? How are these representations transformed? You can see that now we're going to carry in one representation for each context item, for each context word, but those representations are going to be transformed at each layer. And so to understand the transformer, we want to understand how that transformation happens. And there's two main parts of it, the bottom part and the top part. Each of them consists of something followed by a layer normalization, which I'll explain in a moment. Big, really new, conceptually advanced thing relative to what we've seen earlier in the class is this masked multi-headed self-attention. And so that's what I'm going to focus on first. Attention is not something that we've seen before, but it's actually very widely used today in deep learning, and it's a very powerful mechanism, and the transformer uses it to great effect. So to understand attention, it's conceptually useful to think of a dictionary or an inventory of items. Each of those items has a value and a key, and those values and keys are paired. So the first item is going to be V1, K1 pair, and so forth. If we have I-1 entries in the context for a sentence, there's W's 1 through I-1, then we have I-1 key value pairs. In an attention model, you have that collection or dictionary of key value pairs, and then you have a query, a single query. And what the query is going to do is it's going to be compared against the key in some form, and you're going to get some kind of goodness of fit value, which says how much I care about the value corresponding to that key. So if a query matches a key, then I'm very well, then I'm going to use that value a lot. If a query is a poor match to the key, then I'm going to use the corresponding value very little. What that actually means is that we're going to calculate affinity functions. These are sometimes called the E sub j's, and those affinity functions are going to be determined by taking Q and K together and applying some function to it. There are many functions that have been used. The original attention paper was Bodenau et al. 2014. It used a relatively complex function. There are different functions that have been proposed. In the transformer, the original paper was, this is what's called scaled dot product attention. It's called that because the first thing that you'll see here in the numerator, this is a dot product, simply the dot product of the query and the key. And then there's a normalization, the scaling, which is just by the dimensionality, the square root of the dimensionality of the key. And the query and the key, of course, in a dot product model have to have the same dimensionality. Okay. So once we have that E sub j, then we're going to take those and we're going to normalize them into a probability distribution, a proper distribution over the elements in the dictionary. We're going to use this through the softmax function. So we're going to transform the e's into alphas. And softmax is, once again, you just exponentiate each value and you normalize by the sums of the exponentiated values. And so those alphas are going to be, those are what are called attention weights often. And they're going to be how much you weight each of the values. What do you do with those weighted values? Something very simple. You just sum them together. So you take these values, multiply them by the alphas, and your output is just this weighted combination of the values. Okay. So that's neural attention. You use a query, compare it to a whole bunch of keys. The quality of the fit to each, between the key, each key in the query gives you an alpha value between 0 and 1, and the resulting output is a weighted sum of the values in the dictionary where the weights are the alpha values. How is this used in the transformer model? So the transformer has what are called multiple attention heads, and I'm going to show you the behavior of a single attention head. Okay, so let's say that we have 3 words in the context, and we're going to try to predict the next word. So coming in, say at the bottom level, this is the, there's going to be some representation of each word. This might be, for example, starting out the sum of the word embedding and the positional embedding representation. We'll call these x sub i's. So you have x1, x2, x3. There are matrices that are learned during training, wk, wv, wq, which will transform just through a simple linear transformation the x's into queries, into keys and values, and then a query for a particular word. Okay. So, for example, each of the w sub I has a key computed from it with w sub k matrix. With the w sub b matrix, you compute a value, and then now I want to know. Let's say that I'm interested in word 3. How is the representation of word 3 going to be transformed? So first, I use w sub q to compute a query representation of that word. And so now I have Q3, and I'm going to compare it against all the keys. And I'm going to get out through the attention function and normalization through softmax, I'm going to get out some alpha values. Okay. I'm going to use those alpha values then to combine the values from each of the words that were computed with the value matrix applied to the input representation, and I'm going to get an output representation. This is a transformed output representation of word 3, O sub 3. Now, so this is the function of a single masked attention head on this word. You'll see that the word masked is in the title, and I didn't explain that to you before. So masking comes in when I want to ask, what about words that are not the most recent word in the context, but earlier words? So in this case, the masking means that I am not able to attend to words that are following the word in question in the context. So subsequent context words are basically invisible. I cannot use the key or value from x3 when I'm computing the output representation of O2, of word 2. Instead, I will just have, well, first of all, I'll use the query function, the query matrix to compute a value for W2, a query for W2. I'll then compare it to each of the keys of the current and preceding words. And so I'll have only 2 alpha values, and then I'll combine those 2 values to get O2. That's what masked attention means. It means that when I'm computing the representation, the transformed representation for W sub j, I cannot attend to words that for j prime greater than j. So that's a single masked attention head. Now, actually, the transformer has many attention heads. We'll call the number of attention heads h. And it turns out that this just works very well. In principle, the idea is that different attention heads can attend to different kinds of information. Each head will have its own key value and query matrix. And you will, at any particular layer of the transformer, this scaled dot product attention function operates within each of the heads, and you simply concatenate the outputs of each of the heads. And then there's one other learned matrix, W sub O, that linearly transforms the concatenated output. And that's the output of masked multi-headed attention. Okay. So the next thing you see above masked multi-headed self-attention, which is that is the most complicated thing that that we're covering today with transformer. The next thing is layer normalization. This is something, and furthermore, there's another thing here. You'll see that there is this arrow that goes around the masked multi-headed self-attention that goes directly into something that feeds into layer normalization. That's what's called a residual connection. Residual connection simply means that although I'm going to transform the input in some way, I'm also going to pass the input through uninterrupted. And that turns out to work in practice for reasons that are really sort of vanishing gradient reasons. That's the best understanding. But you'll remember that actually we saw something like this in the gated recurrent unit, that we actually sometimes we sort of wanted to have an opportunity to pass information through many transformations. We wanted to have an easy route for that information to propagate unchanged. And there's, in practice, it's probably some combination of both these things that makes this useful. What does this mean? First of all, the residual connection means that simply we compute something that goes into what's called layer normalization, which is just a sum of the output of the masked multi-headed self-attention and the original input. In practice, this can be a weighted sum. In the original transformer model, it wasn't, but some people will make this a weighted sum. So there may be some, there may be a lambda weight, for example, here that is that's learned. This is another option, but it's not actually necessarily done. Layer normalization, then simply, it's a very simple function. It takes these, it takes the input to it and it just standardizes it so that across the individual elements in the vector, so that the mean vector entry will be 0 and the standard deviation is going to wind up being 1. And this is just going to be something that prevents the activation levels of the inputs and outputs from sort of exploding and going off in different directions, which it turns out in practice to help with learning. Okay, so that's residual connection and layer normalization. They're fairly simple things. The next part of the model is this feed-forward layer. This is just a simple, single hidden layer feed-forward network. In practice, the dimensionality of the hidden layer is made larger than the dimensionality of the input of the output. This turns out actually to work quite well in practice. It may be a little counterintuitive, but actually large hidden layers can be very helpful for learning. And then, of course, that feeds again into residual connection and layer normalization in exactly the same way that we saw before. And that is one layer of the transformer. So this is a single layer, but we said before that these models are deep. And so in practice, what we do is we stack these layers. The output of one layer becomes the input of the next layer. And we do this many times over. And that, at the end of the top layer, we do a simple softmax weighted prediction to get a predictive distribution over the next word, or whatever we're trying to predict. And so this is the picture. This is the actual instantiation of the picture of how the transformer plays out this conceptual picture of a deep model that successively transforms words. Words are able to interact with each other, but there's no intrinsic left to right bias in this model, except for one thing, which is in the masking. The masking part of the self-attention actually creates a certain kind of left to right bias because words can only interact with words in the preceding context. So that's the transformer. Now, that model, it turns out, plus a large amount of data, is extremely powerful. And it, in fact, underlies one of the most news-grabbing AI models for language in the past year, which is GPT-2. And this was a masterful stroke by the tech company OpenAI, which a little over a year ago, you may have noticed this, they said, we have generated an incredible AI language model. It can generate text, and it may be able to generate fake text that cannot be distinguished from humans. And this may be too dangerous to release. So we're only going to give you, we're not going to give you the full rich version of it. We're going to give you only stripped down versions of it. Later on in the year, they actually did release this model that they said was too dangerous to share, and now you can actually use it for a lot of different things. We'll take a brief break and then actually look at some actual behavior of this model. But it turns out this is actually a very impressive model in my own view, and it's worth at least playing around with and getting some familiarization with. And this really is the transformer for a variety of reasons. Not only is it flexible in how it attends to the context, but for technical reasons that we're not going to get into, it actually has very favorable training behavior. And this is actually a state-of-the-art model now for a wide variety of applications, and in particular for text generation, GPT-2 is the state-of-the-art.